There is a moment in human history when a single question changes everything. Not a question about the stars, not about the nature of matter, but about something far more intimate, what separates your mind from a machine. This is where Alan Turing enters the story, not as a physicist or an engineer, but as a logician who dared to ask the question that would terrify generations to come. The Turing machine was not invented to build computers. It was invented to answer a question that had haunted mathematics for decades. What can be calculated? What cannot? And in answering that question, Turing stumbled upon something far darker, a terrifying truth about human behavior that we are still running from today. You think you are free. You think your choices are yours. You think your logic is unique, irreplaceable, something that no algorithm could ever replicate. But what if Turing proved that you are wrong? What if the very structure of your thinking, the way you solve problems, the way you make decisions under pressure, follows a pattern so mechanical, so predictable, that it can be written as a sequence of simple instructions? This is not science fiction. This is not speculation. This is what the Turing machine revealed, and it is terrifying because it is true. The promise of this exploration is simple. By the end of this journey, you will understand not just what a Turing machine is, but why its existence forced humanity to confront a question we have been avoiding for centuries. You will see how Turing's abstract mathematical creation became the blueprint for understanding human behavior itself. You will discover that the terrifying human behavior Turing explained is not something external to you. It is something you do every single day, something you cannot stop doing, something that proves you are far more mechanical than you ever wanted to believe. But before we go deeper, let me ask you something that will seem simple, but is anything but. You believe you think. You believe your thoughts are spontaneous, creative, free. But have you ever stopped to consider what thinking actually is? Have you ever examined the process itself, not the content, but the mechanism? Most people have not. Most people assume thinking is something magical, something that emerges from consciousness in ways we cannot understand. But Turing did not accept that assumption. He looked at thinking as a process, as a sequence of steps, as something that could be broken down into smaller and smaller components until you reach the absolute foundation. And when he did that, when he stripped away all the poetry and all the mystery, he found something that should have shocked the world, but instead was quietly filed away in academic journals. He found that human thinking at its core follows rules, not rules that we consciously follow, but rules that are built into the very structure of logic itself. The terrifying part is not that machines can think like humans. The terrifying part is that humans think like machines. And once you see that, you cannot unsee it. You cannot go back to believing that your mind is something special, something beyond the reach of mathematics and algorithm. This is the journey we are about to take together, and it begins with a man who was willing to ask the questions that no one else dared to ask. In the 1930s, mathematics was in crisis. Not a crisis of funding or resources, but a crisis of foundations. For centuries, mathematicians had built their entire discipline on the assumption that mathematics was complete, that every true statement could be proven, that logic was absolute and universal. Then Kurt Gödel came along and shattered that assumption. In 1931, Gödel published his incompleteness theorems, which proved that any consistent mathematical system powerful enough to describe arithmetic contains statements that are true but cannot be proven within that system. The implications were staggering. It meant that mathematics itself was incomplete. It meant that there were truths that existed beyond the reach of proof. It meant that the foundation upon which all of mathematics rested was fundamentally unstable. This discovery sent shockwaves through the mathematical community. If mathematics was incomplete, what did that mean for logic? What did it mean for the very concept of truth? And most importantly, what did it mean for the possibility of creating a machine that could solve all mathematical problems? This is where David Hilbert enters the picture. Hilbert was one of the greatest mathematicians of his time, and in 1928 he posed what became known as the Entscheidungsproblem, or the decision problem. The question was deceptively simple. Is there a mechanical procedure that can determine for any given mathematical statement whether that statement is true or false? In other words, is there an algorithm that can solve all mathematical problems? This question haunted the mathematical world. If such an algorithm existed, it would mean that mathematics could be completely automated, that a machine could be programmed to solve any problem. If it did not exist, it would mean that there were limits to what could be calculated, limits to what could be automated, limits to what machines could ever do. Alan Turing was a young mathematician at Cambridge when he encountered this problem. He was not the most famous mathematician of his time. He was not the most celebrated, but he had something that many of his peers did not have: the willingness to think in completely new ways. While other mathematicians were trying to solve the Entscheidungsproblem using traditional mathematical approaches, Turing decided to approach it differently. He decided to think about what it meant to calculate something. He decided to imagine a machine, a theoretical machine that could perform calculations step by step, following simple rules, moving back and forth on an infinite tape, reading symbols, writing symbols, erasing symbols, and changing its internal state based on what it read. This machine, which would become known as the Turing machine, was not designed to be practical. It was not designed to be built. It was designed to be a thought experiment, a way of formalizing the concept of calculation itself. And in creating this machine, Turing did something remarkable. He created a model of computation that was so simple, so fundamental, that it could be used to answer the question that had been haunting mathematics for years. The Turing machine works like this. Imagine an infinite tape divided into squares, each square containing a symbol, either a 0 or a 1 or blank. The machine has a head that can read the symbol on the current square, and based on what it reads and its current internal state, it can perform three actions. It can write a symbol on the square, it can move left or right along the tape, or it can change its internal state. The machine operates according to a set of rules, a table of instructions that specifies exactly what to do in every possible situation. The beauty of this model is its simplicity. The Turing machine can only do a few things, but those few things are enough to perform any calculation that can be performed by any computer, any algorithm, any mathematical procedure. This is what became known as the Church-Turing thesis. Any function that can be computed by any reasonable model of computation can be computed by a Turing machine. In other words, the Turing machine is universal. It can compute anything that is computable. But here is where the terrifying part begins. If the Turing machine can compute anything that is computable, then anything that a Turing machine cannot compute is, by definition, not computable. And Turing proved that there are things that a Turing machine cannot compute. He proved that there is a fundamental limit to what can be calculated. He proved that there are problems that no algorithm, no machine, no procedure can ever solve. The most famous of these is the halting problem. Turing proved that there is no algorithm that can determine, for any given program and any given input, whether that program will eventually halt or run forever. This might seem like an abstract mathematical curiosity, but it is far more than that. It is a proof that there are limits to computation. It is a proof that there are questions that machines cannot answer. But more importantly, it is a proof that there are questions that humans cannot answer either, because human thinking, at its core, is also a computational process. Now let me tell you about the Enigma machine, because this is where Turing's abstract theory became concrete, where his mathematical insights became weapons of war. During World War II, The German military used the Enigma machine to encrypt their communications. The Enigma was a mechanical cipher machine that used a series of rotating rotors to encrypt messages. Each rotor had 26 positions, one for each letter of the alphabet. The rotors would rotate after each letter was encrypted, changing the encryption key. The number of possible configurations was staggering. With 3 rotors, there were 26 times 26 times 26 equals 17, 576 possible rotor positions. But the Enigma had more than just rotors. It had a plug board that could swap letters before they entered the rotors and after they exited. With the plug board, the number of possible configurations jumped to over 158 quintillion. That is 158 followed by 18 zeros. The British military knew that the Germans were using the Enigma to encrypt their messages, and they knew that if they could break the Enigma, they could read German communications and gain a massive advantage in the war. But how do you break a cipher with 158 quintillion possible configurations? You cannot try them all. Even if you could test one configuration per second, it would take longer than the age of the universe to test them all. This is where Turing came in. Turing understood that breaking the Enigma was not about trying all possible configurations. It was about understanding the structure of the machine, about finding patterns, about using logic to eliminate possibilities. He designed a machine called the bomba, named after an earlier Polish design, that could test multiple Enigma configurations simultaneously. The bomb used electrical circuits to simulate the Enigma machine and could test thousands of configurations per minute. But the bomb was not just a brute force machine. It was a clever machine, a machine that used logical deduction to narrow down the possibilities. It used known plaintext attacks, where a piece of known plaintext could be used to determine the rotor settings. It used the structure of the Enigma machine itself to eliminate impossible configurations. The bomb was so effective that it could break an Enigma message in hours instead of days or weeks. Historians estimate that breaking the Enigma shortened World War II by several years and saved millions of lives. Some estimates suggest that the intelligence gained from breaking the Enigma prevented the German invasion of Britain and changed the course of the entire war. But here is the terrifying part. The bomba was not intelligent. It did not understand German. It did not understand the meaning of the messages it was decrypting. It simply followed a set of logical rules, step by step, testing configurations, eliminating possibilities, until it found the answer. And it was more effective at breaking the Enigma than any human cryptographer could ever be. This is the first glimpse of the terrifying human behavior that Turing explained. Humans are not as good at logical reasoning as machines. We are not as good at following rules. We are not as good at eliminating possibilities. We are not as good at computation. And once you realize that, once you see that a machine can do something better than you can, something that you thought required intelligence and creativity and human insight, you start to wonder what else machines might be better at. Now we move into the deeper waters, the place where Turing's abstract mathematics becomes a mirror held up to human nature itself. The Turing machine was not just a theoretical construct. It was a model of computation that could be used to understand any process that involves following rules, making decisions based on information, and producing an output. And human thinking, at its core, is exactly that kind of process. When you solve a problem, you are following a set of rules. When you make a decision, you are processing information and applying logic. When you learn something new, you are updating your internal state based on what you have learned. You are, in essence, running a program. This is not metaphorical. This is literal. Your brain is a biological computer, and your thoughts are the output of that computer running a program. The program is not written in code. It is written in the structure of your neural networks, in the connections between your neurons, in the patterns of electrical and chemical activity that flow through your brain. But it is a program nonetheless, and like any program, it follows rules. It has inputs and outputs. It has states and transitions. It can be modeled, analyzed, and understood using the same mathematical framework that Turing developed for understanding machines. This is where the terrifying human behavior emerges. The behavior is this: humans are predictable. Not completely predictable, not in every detail, but predictable in the ways that matter. Your decision-making process follows patterns. Your problem-solving approach follows patterns. Your emotional responses follow patterns. Your social behavior follows patterns. And these patterns can be understood, modeled, and even predicted using the same logical framework that governs machines. Consider the halting problem again. Turing proved that there is no algorithm that can determine whether a program will halt or run forever. But humans face the same problem every day. When you are working on a difficult problem, you do not know if you are going to solve it or if you are going to be stuck forever. You do not know if the approach you are taking will lead to a solution or if you are wasting your time. You have to make a decision. Do I keep trying or do I give up? And the way you make that decision is not based on some magical insight or intuition. It is based on heuristics, on rules of thumb, on patterns that you have learned from experience. You estimate how much progress you are making. You estimate how much time you have left. You estimate the probability of success, and based on those estimates, you decide whether to continue or to give up. But here is the terrifying part. Those estimates are often wrong. You often give up on problems that you could have solved if you had kept trying. You often waste time on problems that are unsolvable. You often make decisions based on incomplete information and faulty reasoning. And the reason you do this is because your brain is running a program that is designed to make quick decisions with limited information, not to find optimal solutions. Your brain is running a heuristic algorithm, not an optimal algorithm. And that heuristic algorithm is predictable. It follows patterns. It can be modeled and understood. This is where modern technology comes in, and this is where the terrifying implications of Turing's work become visible in the real world. Artificial intelligence systems, recommendation algorithms, predictive models, all of these are based on the same principle that Turing discovered. Human behavior is computable. It can be modeled. It can be predicted. It can be influenced. When you use a social media platform, you are not just consuming content. You are being studied. Your behavior is being analyzed. Your preferences are being modeled. Your decision-making process is being mapped. And based on that model, the algorithm predicts what content you will engage with, what you will click on, what you will share. And it does this with remarkable accuracy. The algorithm knows you better than you know yourself. It knows what will make you angry, what will make you sad, what will make you click. It knows your vulnerabilities, your weaknesses, your patterns of behavior, and it uses that knowledge to influence your decisions. This is not conspiracy theory. This is not speculation. This is how modern technology works. And it works because Turing was right. Human behavior is computable. It is predictable. It can be modeled and influenced using the same logical framework that governs machines. The terrifying human behavior that Turing explained is not something that emerged recently with the advent of artificial intelligence. It is something that has always been true about humans. We are predictable. We follow patterns. We can be modeled and understood using logic and mathematics. What has changed is that we now have the technology to exploit that predictability on a massive scale. We now have machines that can analyze billions of human decisions and extract the patterns. We now have algorithms that can predict human behavior with uncanny accuracy. We now have systems that can influence human decisions at scale. And all of this is possible because Turing proved that human thinking is a computational process. Consider the concept of free will. For centuries, philosophers have debated whether humans have free will or whether our actions are determined by prior causes. Turing's work suggests that this debate is based on a false premise. Free will is not about being unpredictable. Free will is not about being random. Free will is about being the author of your own decisions, about your decisions flowing from your own values and preferences and reasoning. But if your values and preferences and reasoning can be modeled and predicted, does that mean you do not have free will? This is the question that Turing's work forces us to confront. And the answer is not simple. It is not yes or no. It is something far more subtle and far more terrifying. Your decisions are determined by your internal state, by your values, by your preferences, by your reasoning, but your internal state is not fixed. It is constantly changing based on your experiences, based on what you learn, based on how you interact with the world. So in a sense, you are free. Your decisions are your own. They flow from your own reasoning and your own values. But at the same time, your reasoning and your values are computable. They follow patterns. They can be modeled and predicted. So in another sense, you are not free. Your decisions are determined by a process that can be understood and modeled using logic and mathematics. This is the paradox that Turing's work reveals. You are both free and determined. You are both unique and predictable. You are both human and machine. And that is terrifying because it means that the boundary between human and machine is not as clear as we thought. It means that the things we thought made us special, the things we thought made us human, are actually computable processes that machines can replicate. It means that the gap between human intelligence and machine intelligence is not as wide as we believed. The implications of this realization extend far beyond philosophy and into the realm of practical human behavior. Consider how you learn. When you learn something new, you are updating your internal model of the world based on new information. You are adjusting your beliefs, your expectations, your understanding of how things work. This process is computable. It can be modeled using Bayesian inference, using neural networks, using machine learning algorithms. And indeed, modern machine learning systems learn in remarkably similar ways to how humans learn. They take in data, they extract patterns, they update their internal models, they make predictions based on those models, and they often learn faster and more accurately than humans. Consider how you make decisions under uncertainty. When you face a decision where you do not have complete information, you use heuristics, you use rules of thumb, you use patterns that you have learned from experience, you estimate probabilities, you weigh costs and benefits. This process is computable. It can be modeled using decision theory, using game theory, using algorithms that optimize for expected utility. And machine learning systems can learn to make decisions in the same way that humans do, often with better results. Consider how you interact with other people. Your social behavior follows patterns. The way you communicate, the way you build relationships, the way you cooperate and compete, all of these follow predictable patterns. And these patterns can be modeled and understood. This is why social media algorithms are so effective at predicting what content you will engage with. This is why recommendation systems can predict what products you will buy. This is why political campaigns can target you with messages that are designed to influence your behavior. All of this is possible because human behavior is computable. But here is the crucial insight that Turing's work provides. Just because something is computable does not mean it is simple. Just because human behavior follows patterns does not mean those patterns are easy to understand. The human brain is the most complex system we know of. It has approximately 86 billion neurons, each connected to thousands of other neurons, creating a network of staggering complexity. The number of possible states of the human brain is larger than the number of atoms in the universe. So, while human behavior is computable in principle, it is not computable in practice. We cannot predict every detail of human behavior. We cannot model every nuance of human thought. We cannot fully understand the human mind using current technology, but we can understand the broad patterns. We can predict behavior in aggregate. We can identify the heuristics that humans use. We can model the decision-making process. And we can use that understanding to influence behavior. This is the terrifying human behavior that Turing explained. We are predictable enough to be influenced, but complex enough that we do not fully understand ourselves. We are machines, but machines so complex that we cannot fully comprehend our own nature. We are computable, but so computationally expensive that we cannot compute ourselves. And this creates a fundamental asymmetry. Machines can understand us better than we understand ourselves. Algorithms can predict our behavior better than we can. Systems can influence our decisions in ways that we do not fully comprehend. And all of this is possible because Turing proved that human thinking is a computational process. The question that haunts us now is this: what happens when machines become better at understanding human behavior than humans are? What happens when algorithms know us better than we know ourselves? What happens when systems can predict and influence our decisions with near-perfect accuracy? Turing did not live to see the age of artificial intelligence. He died in 1954 at the age of 41 under circumstances that remain controversial. But he left behind a legacy that has shaped the entire trajectory of human civilization. He proved that computation is universal. He proved that machines can do anything that can be done by following rules and processing information. He proved that human thinking is a computational process. And in proving all of this, he revealed a terrifying truth about human nature. We are not as special as we thought. We are not as free as we believed. We are not as unique as we imagined. We are machines. Biological machines, yes, but machines nonetheless. And like all machines, we are predictable. We follow patterns. We can be modeled and understood. We can be influenced and controlled. This is the terrifying human behavior that Turing explained. It is not a behavior that emerged recently. It is not a behavior that is unique to modern technology. It is a behavior that has always been true about humans. We are computable. We are predictable. We are machines. And once you see that, once you understand that, you cannot unsee it. You cannot go back to believing that your mind is something magical, something beyond the reach of mathematics and algorithm. You cannot pretend that you are fundamentally different from a machine, because Turing proved that you are not. He proved that the difference between human and machine is not a difference in kind, but a difference in degree. It is a difference in complexity, in the number of states, in the sophistication of the algorithm. But it is not a fundamental difference. It is not an unbridgeable gap. It is a difference that machines are rapidly closing. The implications of this realization are still unfolding. We are living in the age of artificial intelligence, an age that Turing helped to create. We are surrounded by machines that can recognize faces, understand language, play games, make decisions, and influence behavior. These machines are based on the principles that Turing discovered. They work because human behavior is computable. They succeed because they can model and predict human decision-making. They influence us because they understand the patterns of human thought. And as these machines become more sophisticated, as they learn more about us, as they gain more power to influence our behavior, the implications of Turing's discovery become more and more apparent. We are not the masters of our own minds. We are not the authors of our own decisions. We are running programs that we did not write, following rules that we did not choose, making decisions based on heuristics that we do not fully understand. And machines are learning to exploit that fact. They are learning to predict us. They are learning to influence us. They are learning to control us. And they can do this because Turing proved that we are machines. Biological machines, yes, but machines nonetheless. And machines can understand other machines. Machines can predict other machines. Machines can control other machines. This is the terrifying human behavior that Turing explained. It is not a behavior that we can escape. It is not a behavior that we can deny. It is a behavior that is fundamental to human nature. We are computable. We are predictable. We are machines. And that is the most terrifying truth that mathematics has ever revealed about the human condition.